Imagine you could control the flow of light in ways never before thought possible, like flipping the switch on an entire new era of optical devices. Well, that's exactly what a groundbreaking development has brought us closer to achieving. The world's first photonic time crystal. In 2017, theoretical physicists laid out the blueprint for these revolutionary structures, but it wasn't until 2019 that researchers managed to turn this idea into reality. This wasn't just about creating a new kind of material, they were essentially weaving temporal patterns like a never-ending loop in time into light waves. These photonic time crystals can be engineered to control the temporal properties of light, much like how traditional photonic crystals manipulate spatial properties. Photonic time crystals are built on an ingenious idea. By introducing periodicity not just in space but also in time, they open up a whole new playground for light manipulation. Think of it as the 3D version of spatial crystals. In these structures, the optical properties of light change periodically with time, creating a dynamic and flexible environment. Imagine you have a line of atoms arranged in a repeating pattern, like beads on a string. Now, imagine those beads are not only spaced apart but also vibrate at regular intervals. That's what a photonic time crystal is, but for photons. By introducing these periodic changes over time, scientists can create optical effects that don't exist in conventional materials. Detailed mechanism and examples to fully grasp how photonic time crystals work. Consider the following example. In one experiment, researchers created a lattice of atoms where light waves propagate through it. Normally, as they move forward, these light waves experience different interactions with the atoms, causing them to change direction or phase. However, in a photonic time crystal, scientists use lasers and carefully timed pulses to create a temporal lattice that changes periodically over time. This periodicity can be designed such that certain wavelengths of light are allowed to pass through while others are blocked, depending on when you look at the system. For instance, imagine a scenario where you have a series of optical lattices placed in sequence. Each lattice introduces its own periodicity, creating a complex but predictable temporal pattern. Potential applications beyond telecommunications. The potential implications of this technology are mind-boggling. For instance, these structures could be used to develop novel nonlinear optical effects that enhance the interaction between photons. Imagine being able to create devices where light waves interact with each other in ways previously thought impossible. This could lead to advancements in laser technologies, sensors, and even new types of quantum computers. Moreover, the ability to control the temporal properties of light opens up possibilities for ultra-fast signal processing. In today's world of high-speed computing, this means we might be able to process data faster than ever before. The implications for fields like cryptography, where speed is crucial, are immense. Traditional photonic crystals rely on spatial periodicity to manipulate light waves, creating bandgaps where certain wavelengths of light are trapped or forbidden. But with photonic time crystals, we're not limited by these spatial constraints anymore. This opens the door to completely new phenomena and applications that were previously unimaginable. Advancements in optical devices. One such application is ultra-low-loss optical delay lines. You know how data packets travel through fiber optic networks? Well, in those networks, there's always some loss due to heat or other factors. But with photonic time crystals, scientists can create a kind of time tunnel where light travels without losing much energy. This could revolutionize everything from telecommunications to quantum computing. In the realm of quantum information processing, photonic time crystals could play a crucial role. Quantum computers rely on delicate interactions between particles at specific times and places. By using photonic time crystals, researchers can precisely control when and how photons interact, leading to more robust and stable qubits. This could be transformative for developing practical quantum computing technologies. Real-world implications. The potential benefits of these new materials are vast and varied. For example, integrating photonic time crystals into existing optical networks could create ultra-fast communication systems that are both secure and energy efficient. The ability to manipulate light at will opens up possibilities for creating entirely new types of sensors and imaging devices. Moreover, the implications extend beyond technology. Photonic time crystals can be used in fields like biophotonics, where precise control over light interactions is crucial for analyzing biological samples or medical treatments. In materials science, these structures could enable the creation of new kinds of photonic metamaterials with unprecedented properties. To understand how these crystals work, let's break it down a bit more. Essentially, the researchers create an optical lattice that changes periodically over time. This means that at different moments in time, light behaves differently within this lattice. For example, they might set up a system where certain wavelengths of light are allowed to pass through while others are blocked, depending on when you look. This isn't just theoretical. Experiments have shown these crystals can indeed manipulate the flow of light in precisely controlled ways. Scientists use lasers and carefully designed optical fibers to create the temporal lattice, ensuring that light behaves according to their needs. Experimental setup. The experimental setup typically involves using a series of microwaves or lasers to create the periodicity in time. For instance, researchers might place an array of atoms or defects in a material and then apply a sequence of pulses from a laser. These pulses create a temporal lattice that changes over time, allowing light to propagate through the system in specific ways. One notable experiment involved using a microcavity with a photonic crystal. By applying a series of microwave pulses, scientists could engineer the cavity such that certain frequencies of light were allowed to pass, while others were absorbed or reflected. This created a dynamic environment where light behaved differently depending on the timing and sequence of these pulses. Challenges and future prospects. Of course, as with any new technology, there are challenges. One major hurdle is scaling up these structures so they can be used practically. The current designs work on a microscale, but achieving macroscopic devices will require overcoming significant engineering challenges. Additionally, the control mechanisms need to become more efficient and reliable. Despite these hurdles, the potential benefits make it worth pursuing. Imagine integrating photonic time crystals into existing optical networks, creating ultra-fast communication systems that are both secure and energy efficient. Or envision quantum computers, where light plays a central role in processing information at unprecedented speeds. The development of photonic time crystals marks the beginning of a new era in photonics. By introducing temporal periodicity to the spatially periodic structures of conventional photonic crystals, these materials open up a whole new world of possibilities for light manipulation. From ultra-low-loss optical delay lines to novel nonlinear optical effects and beyond, the applications are vast and varied. As we continue to explore this fascinating field, one thing is certain: the future of photonics is about to get even more exciting. Whether it's revolutionizing telecommunications or enabling quantum computing breakthroughs, photonic time crystals could very well be the key to unlocking a brighter technological future. In conclusion, photonic time crystals represent a paradigm shift in how we manipulate light. By combining spatial and temporal periodicity, these materials open up new avenues for creating optical devices with unprecedented capabilities. From ultra-fast signal processing and quantum computing to revolutionary communication systems and advanced sensors, the potential applications are countless. As research progresses, expect to see these structures integrated into various fields, transforming our technological landscape in ways we can only begin to imagine. The future is bright, and photonic time crystals are at the forefront of that future.